Welcome to Quantum, the channel where we explore the deep and intricate world of mathematical, theoretical, and philosophical physics, everything quantum. Today we delve into one of the most fascinating phenomena in condensed matter physics, the Hall effect and Landau levels. More than just an experimental discovery, this is one of the most fundamental quantum systems in theoretical physics, revealing deep connections between gauge symmetries, topology, noncommutative geometry, and the quantum nature of electrons in a magnetic field. This lecture is structured into 5 segments. 1. The Hall effect, its discovery by Edwin Hall and its classical implications. Landau energy levels, the quantization of electron motion in a magnetic field. 3. Wave functions and degeneracy, how gauge choices reveal the highly degenerate nature of Landau levels. 4. The noncommutative plane, the deep connection between Landau levels and quantum geometry. 5. The lowest Landau level, the role of holomorphic functions and the structure of quantum states. Join me as we explore the interplay between electromagnetism, gauge symmetries, and quantum mechanics in this fundamental system. Hall effect. In the first segment, we explore the discovery of the Hall effect by Edwin Hall in 1879. The Hall effect occurs when a current flows in the x direction under a perpendicular magnetic field in the z direction, leading to the induction of a voltage in the y direction due to the Lorentz force acting on the charge carriers. Specifically, the Lorentz force pushes electrons in the positive y direction, causing them to accumulate at one end of the conductor, while the opposite end becomes more positively charged. This charge separation generates an electric field directed from the positive to the negative charges, meaning the induced Hall electric field points in the positive y direction, opposing the motion of the electrons. At equilibrium, the electric force cancels out the Lorentz force, resulting in a steady Hall voltage along the y direction. In this state, electrons maintain a constant velocity in the x direction, while their motion in the y direction stops, as the forces acting on them are balanced. A reasonable model for describing the Hall effect is the Drude model, which incorporates also the effect of friction due to scattering, allowing us to derive Ohm's law and the resistivity tensor. In this framework, the off-diagonal components of the conductivity tensor sigma represent the Hall effect, a current flowing in the x direction under the effect of a perpendicular magnetic field in the z direction induces a voltage in the y direction. Landau energy levels. In the second segment, we analyze a point particle of mass m and charge -e moving in the xy plane under an electromagnetic field, described by scalar and vector potentials that define the electric and magnetic fields in the usual way. These potentials form the electromagnetic gauge field. We derive the system's Lagrangian, showing that the resulting Euler-Lagrange equations correspond precisely to the Lorentz force. Under gauge transformations, the Lagrangian changes only by a total derivative, ensuring gauge invariance of the physics, an essential feature of our discussion. For the remainder, we will align the magnetic field along the z direction and set the scalar potential to 0. The effect of the electric field will be considered at the end. From the Lagrangian, we identify the generalized momentum conjugate to the particle's coordinate and establish the fundamental Poisson brackets. Expressing the Hamiltonian in terms of these canonical coordinates and momenta reveals that the system's energy depends on the gauge non-invariant mechanical momentum rather than the gauge invariant conjugate momentum. We also determine the Poisson brackets of the mechanical momentum with the coordinate and conjugate momentum. Upon transitioning to the quantum theory via canonical quantization, we replace the coordinates, generalized momenta, and mechanical momenta, as well as the Hamiltonian, with corresponding operators acting in a Hilbert space. The Poisson brackets are replaced by commutators divided by I times h bar, yielding the Dirac-Heisenberg fundamental commutation relations. Since the Hamiltonian depends on the mechanical momentum, we also establish the commutators for its operators. Notably, these relations resemble the algebra of quantum harmonic oscillators, and thus we can express them in terms of raising and lowering operators. The Hilbert space is then constructed from a ground state annihilated by the lowering operator, while excited states arise by applying powers of the raising operator to this ground state. The Hamiltonian itself is formulated in terms of the number operator, which directly yields the well-known Landau energy levels when acting on these states. Landau wave functions and degeneracy of Landau levels. In the third segment, we derive the wave functions associated with each Landau energy level and explicitly show that these levels are highly degenerate, requiring us to fix the gauge. We choose the Landau gauge such that translational invariance is broken in the x direction but preserved in the y direction. Since translational invariance remains in the y direction, the wave functions must be eigenfunctions of the momentum operator in the y direction, which is the generator of translations along y. The corresponding eigenvalues are given by h bar times the momentum k in the y direction. In other words, the wave functions must include a plane wave factor associated with propagation in the y direction. By substituting this ansatz into the Schrödinger equation, the problem reduces from 2 dimensions to 1. For each value of k, the Hamiltonian corresponds to that of a quantum harmonic oscillator, shifted from its usual center by minus the magnetic length squared times k. Consequently, the complete wave functions involve shifted Hermite polynomials of the quantum harmonic oscillator multiplied by a Gaussian factor. These wave functions take the form of elongated strips extending along the y direction while being exponentially localized in the x direction around minus the magnetic length squared times k. We then compute the number of states associated with each energy level in a rectangular region of surface area A in the xy plane, where the sides are Lx and Ly. Since y is restricted to the range Ly, the momentum k must be quantized at the same time because the wave functions are exponentially localized around minus the square of the magnetic flux times k, and x is restricted to the range Lx. K itself is limited between minus Lx divided by the square of the magnetic flux and 0. This results in the number of states in the surface area A being given by A times the magnetic field divided by the quantum of flux. The noncommutative plane. Another important gauge choice is the symmetric gauge, which enables us to determine the degree of degeneracy of Landau levels using the Heisenberg uncertainty principle. This gauge also reveals the deep connection between Landau levels and the noncommutative plane. In the fourth segment, we demonstrate that in the symmetric gauge, the mechanical momentum and the center of orbit coordinate form 2 independent sets of harmonic oscillator operators that commute with each other. The mechanical momentum determines the principal quantum number n, which labels the Landau energy levels, while the center of orbit coordinate defines an additional quantum number m that directly corresponds to the degree of degeneracy. This extra quantum number can be interpreted as the angular momentum quantum number. Furthermore, the center of orbit coordinates satisfy the algebra of the noncommutative plane. Consequently, by applying the Heisenberg uncertainty principle, each quantum state occupies a Heisenberg cell. The number of states within an area A of the xy plane is then obtained by dividing this area by the area of a Heisenberg cell, yielding the correct result. The lowest Landau energy level. In the fifth segment, we continue working in the symmetric gauge. We have already established that in this gauge, there exist 2 independent and commuting sets of quantum harmonic oscillator operators, one associated with the mechanical momentum and the other with the center of orbit coordinates. Each set has its own raising and lowering operators, denoted as hat A dagger, for the mechanical momentum, and hat B dagger, for the center of orbit coordinates. Consequently, a quantum state is labeled by 2 integers, n and m, corresponding to the number operators of these 2 sets of harmonic oscillators. As discussed earlier, the quantum number n, associated with the variables hat A dagger, of the mechanical momentum, defines the principal quantum number that labels the Landau energy levels. The additional quantum number m, associated with the variables hat B dagger, of the center of orbit coordinates, corresponds to the angular momentum quantum number. Next, we transition to the complex plane and express these two independent and commuting sets of raising and lowering operators in terms of the complex variable z, defined as x minus I times y, and its conjugate z bar, defined as x plus I times y, along with their corresponding holomorphic and anti-holomorphic derivatives, partial z and partial z bar. We then determine the states of the lowest Landau level, corresponding to n equals 0, by imposing the requirement that they must be annihilated by the lowering operator hat A associated with the mechanical momentum. The ground state within the lowest Landau level must be annihilated by both lowering operators, hat A and hat B, corresponding to the mechanical momentum and the center of orbit coordinates, respectively. The resulting wave function takes the form of a Gaussian factor with a width equal to 2 times the magnetic length squared. The excited states within the lowest Landau level are obtained by applying powers of the raising operator hat B dagger to the ground state. The corresponding wave functions take the form of holomorphic monomials multiplied by a Gaussian factor. By considering linear combinations of these holomorphic monomials, we find that the general wave functions associated with the lowest Landau level, or LLL states, are given by the product of an arbitrary holomorphic function and a Gaussian factor. Conclusion. From Edwin Hall's 19th century discovery to the quantum foundations of noncommutative geometry, we've uncovered the elegant structure of electrons in a magnetic field, one of the most fundamental quantum systems in physics. If this journey through quantum theory intrigued you, don't forget to like, subscribe, and share your thoughts in the comments. Stay tuned for more deep dives into the mysteries of the quantum world, because physics is not just about equations, it's about unveiling the very fabric of reality. See you in the next one.